Okay, so what we've got now is the case where the lambda is greater than 0. So this, in physics terms, this means that the energy of the electrons is positive and they're not trapped by this delta function. Remembering that while we pointed upwards, the potential itself is pulling it down. It's trapping it. All right, we've turned the sign around from the way you probably normally think about it, because you think a potential well should go down. All right, so let's start with our equation. Plus u naught delta of x w equals minus lambda w. Okay, so lambda is greater than 0, so now lambda is equal to k squared. Okay, so remember our k is changing a bit here. All right, so as long as x is not equal to 0, the equation is just the x derivative of w is equal to minus k squared w. So w must be equal to a e to the ikx plus b e to the minus ikx. And there's no way of saying one of these a's or b's have to be 0. In fact, we can't normalize these eigenfunctions either. So it's a bit strange. This is because this corresponds to continuous spectrum and all kinds of stuff. But let's just keep this, think about this thing here. So we're going to write it. So w is equal to a e to the ikx. So this is if x is greater than 0, and we're going to do the same thing, solve on either side of 0 and glue them together. X is less than 0, and if x is greater than 0, we've got the same thing. X is less than 0. Now, obviously these aren't the same. That's the key point. And we're going to get, when we glue them together, we're going to get two conditions as before. We have w at 0 minus is w at 0 plus. Okay, so these are the two conditions. And then we have this condition about the jump. Okay, minus the x derivative of w at 0 minus is equal to, and this is minus u naught w at naught. Okay, so those are the two conditions that we're going to use. This only allows us to specify, if we think about it, we've got 4 constants here. We got rid of 2 of them before because we said it had to decay going away from out to infinity, plus or minus infinity, but here we can't get rid of the constant. So what we do is a bit strange in some senses, is we have to specify an incident condition and an incident wave and a reflected wave. So we say that this is 1. So we have this thing, and this thing here is the incident wave. Change colour to purple, right? That's the incident wave. So what we've got, if we look at the picture here, here's the delta function. We have a wave coming in here. You can ask why it's minus for coincident, but it's convention. And then coming back, we have a reflected wave. And then we have a transmitted wave. So effectively, we're applying boundary conditions at infinity, that the wave is only allowed to come in from the right, from the left with unit amplitude. Okay, so this becomes, get rid of that. I should have had an I here, just notice that error. Okay, so that becomes, yep, R, that should have an I here. All right, and then we get rid of that. We're not allowed waves to come from positive infinity, only from negative infinity, and this becomes, whoops, too much rubbing out. This becomes equal to e to the minus ikx times chi. So now we've only got 2 constants, and we determine those constants, and we're going to be able to solve this no matter what the k is. There's no homogeneous. This incident wave here also makes the system non-homogeneous. So we can't have r is equal to 0, t is equal to 0 is not a solution. Okay, so what happens when we solve this? Well, we get, from here, we get r plus 1 equals t. R plus 1 equals t. And this equation here tells us that the derivative here is minus IKT. And then we've got to be slightly careful here, minus IKR plus IK is equal to minus U0 times W at 0, and because these are equal here, so we might as well put this as T. So that's one equation, and that's another equation, and we have to solve those two equations to get a value for R and T. It doesn't look too scary, does it? Okay, now I'm going to go and solve those equations. What the heck? Let's write them out again here. So we had, you could, normally I expect to say, here's the answer, but I might as well work it out. Okay, so we just substitute here that R is t minus 1, t is whichever one we want here. So we're going to get minus IK, t is 1 plus R, minus 1 plus R U0. And then we put all the r's on one side, and we've got minus IKR, minus IKR, we've got minus IK here, plus IK, so that's going to disappear. We've got minus 2 IKR, and then we've got minus RU0, so that's going to be plus R times U0 is equal to, and then there's, all we're left with is this minus U0. So R is equal to U0 over 2IK minus U0. Correct. And then T is equal to 1 plus R, so it's 2IK minus U0 over 2IK minus U0, that's 1. Reasons for writing that will become obvious in 1 second. Minus 2IK U0, and then of course that adds together, we get minus minus U0, so we get 2IK over 2IK minus U0. Alright, brilliant. And there's some interesting properties of this equation here that we solved here, but we've solved is the key. But the modulus of R squared plus the modulus of T squared is equal to 1. You take the squared and you get units. You can see that from one of them is a real and imaginary part of the denominator. All right, so that's the conservation of energy. Effectively. All right, so that's the end of that solution. So for the, and notice that we have a solution here. We get a solution for every k. Okay, so this, which is, and remember that k is equal to the square root of lambda. Okay, so for every lambda. And that's, so basically, just to maybe just recap quickly when we, just to make this really clear, let's clear this off. So what we found is, we found that for lambda less than 0, we have one solution. Now, sometimes you'll see you can get multiple solutions, but there's always a finite number in these problems. And for lambda greater than 0, we get solution for all lambda. But they're quite different in character, okay? These are finite, right? You know, or decay maybe is a better word, right? Okay, this is, you know, goes to infinity. Okay, so they're quite different in character. All right, I'm going to leave it there.